Hi everyone, my name is Daniel Severo, and today James and I will be talking to you about compressing multisets with large alphabets. So first let's talk about the problem setting that we're interested in. We're given a sequence of IID symbols with entropy h of x to the n, which is the usual entropy term, and we're interested in losslessly compressing the multiset of these symbols to the rate of h of m, so its entropy. So the idea here is that you basically take the symbols in the sequence and you build the multiset, which is just a set that allows repetition of elements. So essentially this is also equivalent to you wanting to encode the sequence, but you don't care about the order in which the symbols are encoded. All you care about are the occurrence counts or the frequency counts of the symbols in that sequence. And that's exactly what the multiset is. So we're interested in compressing the multiset to h of m. So how can we actually do this? How can we actually come up with a scheme to compress m? This has been discussed previously in the literature, and there are methods that are optimal for any alphabets. So for example, one way is to do a frequency count of the symbols in the multiset and compress the integer representing the frequency counts. And you would need to do this once for each element in your alphabet. So it's kind of like building a vector of the size of the alphabet and iterating over it while you encode each element. Now, this is inefficient if your alphabet is too large, basically because you need one step for each element in the alphabet. Alternatively, what you could do is you could forget about the multiset problem and just encode the sequence, because the sequence does contain all of the information for you to rebuild the multiset. This is efficient because if the xi's, the symbols, RIID, then you just need to do a regular entropy coding with the distribution using, for example, arithmetic coding, and that would require roughly pretty much one step per symbol, so n steps. But of course, this is suboptimal because you'll reach the entropy of the sequence and not the entropy of the multiset, which is what we want. So at the end of the day, what we're looking for, which is what we came up with in our method, is something that can efficiently, in a computational sense, encode the multiset and is also optimal. It reaches the entropy of the multiset and it works for any alphabet and any sequence length. So to understand how we actually achieved this, we need about 3 key pieces of background information first. And the first of which is something called asymmetric numeral systems, or ANS. So ANS is just an alternative to arithmetic coding. And let's try to see how they differ. So for example, if you want to encode a symbol using the distribution p of x and this cumulative distribution f of x, both arithmetic coding and ANS use the range statistic of that symbol to perform encoding. However, arithmetic coding, the state of arithmetic coding is represented by a fractional number, while the state in ANS is represented by an integer. And the last aspect we'll take a look at, which is what we're mostly interested in, it has to do with the order in which symbols are encoded and decoded into these two entropy coders. So in arithmetic coding, it's more like a queue, while in ANS, it's more like a stack. So what exactly do we mean by this? The key difference is that ANS decodes in reverse order. So here we can see this in this diagram here. So on the left, we have a diagram for ANS, and on the right, we have a diagram for arithmetic coding. And these blocks here basically represent the bits that have been encoded or are being decoded into the state. So for ANS, it would be an integer, and for arithmetic coding, it would be a fractional number. So you'll notice here that, for example, the first symbol you encoded in arithmetic coding, y1, it will be the first one to be decoded. But in ANS, the first symbol that you encoded will actually be the last one to be decoded because it works in reverse order. And in this diagram, we're here representing the size of the stack or the length of the queue by the entropy of these symbols. So let's keep this diagram at the back of our heads because we'll be using it extensively throughout the talk. So the other background we need is something called bits-back coding, more specifically the variant that uses ANS, BBANS. So BBANS solves a very specific problem, which is given 3 random variables, y equals xz, you want to encode x at the rate of h of x, but you only have a code for the other 2 random variables. So you have a code for y that encodes y optimally, so encodes x and z together, And you have a code for Z conditioned on X. So the code for Z depends on the specific value of X, and it encodes to the conditional entropy of Z given X. So again, you're only interested in encoding X. You don't care about the other two. It just so happens that for some reason you only have a code for the other two random variables. So BBANS actually solves this problem. It can encode X to the entropy if you have access to a sequence of IID X's. In other words, it's a block code. And asymptotically, as n tends to infinity, the rate will reach h of x. And the basic idea is that you use the ANS state, or the ANS stack, as a random seed to sample z's, which you then pair up with the x's, and you use the code for y to encode them on the stack. So let's go through an example here to see exactly how this works. This diagram is very similar to the previous one, where we compared ANS and arithmetic coding, and it's showing basically one stack of ANS evolving over time as we encode x1 and then x2. So the first thing you do is you start off with an empty stack, which isn't shown here, and then you pick a Z1. You pick any Z1 that you want in this first step. It doesn't matter. You can use maximum likelihood, you can sample a random Z, you can pick the first one in the alphabet, it doesn't matter. So after you've picked Z1, you encode it onto the stack together with X1 using the code for Y. Now, after you've done this, you're left here with the stack with some bits on the stack, and you're going to do a decode step. You're going to perform a decode operation with the code for Z so that you can obtain some value for Z2. Now, here we're representing basically the change in length of the stack. So, because we're doing a decode, right? So we're consuming bits, and the bits that are being consumed are basically the bits that make up Z2 here. So after we've performed this step, we're basically left with these fewer bits here on the stack, and now we have some value of Z2. And now what we're going to do is we're going to pair that up with X2, and we're going to encode it on the stack using the code for Y. So this step here, basically it gives us a reduction in the rate. So it allows us to let the ANS stack decide which Z's will appear so that we can pair them up with the X's. And by doing that, you'll notice that once we encoded X2, going from here to here, the size of the stack increases by exactly the entropy of X. And this is the key point to proving that this method works. So, as we mentioned before, the decoding procedure just follows in reverse order. So it exactly inverts what the encoding step did. So for example, we start off here on the right side with x2, z2 on the stack, and we do a decode so we can recover x2 and z2. And now that we have z2 and x2, we basically perform an encode so that we can reverse the decode that happened before in the encoding procedure to put these bits back onto the stack so that we can now recover x1 and z1. So it's pretty straightforward. And if we look at the overall picture, the full picture, if we join those two steps, the decoding and the encoding, into a single step, it'll more or less look like this. You simply encode the pairs x1, z1 onto the stack, and each time you do this, the stack increases by exactly the entropy of x, and eventually you're left with all your symbols on the stack, and basically the rate here will tend to be h of x, and will be off basically by this one-time overhead proportional to the conditional entropy. So this one-time overhead is basically because the first z that you chose wasn't sampled. So we didn't consume anything from the stack, so we didn't get a reduction because the stack was empty to begin with. There wasn't anything to consume. But this one-time overhead will fall to zero as we encode more and more symbols, so it asymptotically does reach the rate of h of x. And decoding, as I mentioned before, just perfectly inverts these steps, so it just does the inverse procedure. Now, the takeaway message here for BBANS is that in the same sense that, for example, entropy gives kind of an operational meaning to lossless compression, for example, BBANS gives an operational meaning to this identity. So you're interested in compressing X, but you don't have a code. So you go into the domain, you augment your symbol to XZ, for which you do have a code, and then you get a discount from using bitsback for the code for Z. So you'll alternate between these two steps, encoding the tuple XZ, which we called Y, and decoding Zs to get the reduction. And then as you do this, you'll reach h of x. So this is kind of the takeaway message of BBANS. Now, the last thing that we need to see is how does the entropy of the multiset relate to the entropy of the sequence? We know that it's at most the entropy of the sequence because the multiset is a function of the sequence. So by using that, using that fact, we know that this conditional entropy term here has to be 0 in this expansion. And then we simply rearrange the terms and we come to the expression of the multiset. So the entropy of the multiset is just the entropy of the sequence minus this conditional entropy term. So what is this conditional entropy term? This can be interpreted as the number of bits that are needed to order the symbols in the multiset to create the specific sequence that you want. So this is sometimes also called the order information or the permutation information. And now, given this, I will hand off the talk to Jamie so that he can present our method, experiments, and conclusions.
Hi everyone, my name's James Townsend and I'm going to talk through our method and our experiments. Firstly, a quick recap of what Daniel said in the first part of the presentation. So we have this idea, BBANS, which gives operational meaning to the identity that says that the entropy of a source X is equal to the joint entropy of X and Z minus the conditional entropy of Z given X. We also have this expression for the entropy of a multiset, which looks pretty similar to the expression at the top. And this suggests a naive method where we simply directly apply BBANS to multiset compression. This is something that we can do, and it would achieve the rate we want on a sequence of multisets. But if you remember at the start of the presentation, what we're really interested in is achieving a rate equal to the entropy of a multiset for a single multiset, not a sequence. And this is equivalent to compressing a multiset down to its information content. That's the problem we're really interested in. We have come up with a way of doing this, and this is kind of a form of BBANS. What we do is we construct the order information iteratively by sampling without replacement from the multiset. To be precise, we alternate between these two steps. Step one is to decode a sample without replacement from M, basically decoding a choice of element, and then encode the sampled element using the distribution P sub x until the multiset is depleted. So I've got a picture to illustrate this. On the left is a ANS stack, on the right is a multiset which we're going to encode, and at the bottom here I'm going to keep track of the height of the stack after each step. So we start with some information in the stack and then we decode a choice of element. Now the stack has chosen a letter B. There are 2 B's in the multiset and 3 elements in the multiset in total. So there was a 2/3 probability of choosing the letter B. So that decoding step reduces the size of the stack by log of 1 over 2/3. Having chosen B, we then remove it from the multiset and push it onto the stack. That increases the stack size by log of 1 over P sub x of B. Then we just repeat. So the multiset's only got 2 elements now. Each one has probability of half of being chosen. The stack this time has chosen the character A, and then we encode A, which increases the stack by P sub x of A. Finally, we decode the last choice. Now you'll notice that log of 1 over 1 is equal to log of 1, which is actually equal to 0. So this is actually kind of a trivial choice that wouldn't actually affect the height of the stack. So the picture's slightly misleading there, but anyway, then we encode that final symbol onto the stack. I put a power of 2 here to keep things compact. So then just kind of gathering terms at the bottom and expressing things in a slightly more general form, we can see that basically this process has encoded those symbols at a rate equal to the information content of the multiset plus this epsilon, which is a constant. So that's pretty good. So as the size of the multiset grows, the constant epsilon becomes irrelevant. So that's our method, and we've applied it to a few different things. Firstly, synthetic multisets. This was a kind of toy experiment just to check that the idea basically worked. And we show here that for various different multiset sizes and alphabet sizes, the algorithm does indeed compress a multiset at a rate very close to the information content of the multiset, or the entropy of the multiset, I should say. Then we were also interested in computational complexity in this paper, because that was kind of the point. We knew there was already a slow way of achieving this. We wanted a faster way. So we timed the encoding and decoding processes and showed that we have decoupled the compute time from the alphabet size. And also that the compute time is roughly linear in n, the multiset size, which is what we'd expect. So that's nice. So then we demonstrated the method on a few other data types, starting with images. And I want to emphasize here that it would not have been possible to use the previously existing methods on images where the compute time scaled with alphabet size, because here the alphabet is effectively the space of all possible images, which can't be enumerated in practice because its size is exponential in the number of pixels in the image. So it would be doable for very, very small images, but not for the images we were evaluating on. And also that you can kind of use any codec as the sort of symbol codec in this method. We used WebP, which is a kind of standard lossless image codec. And we evaluated on a fairly large data set of small-ish images. They're 28 by 28 grayscale images. And you kind of get the result you'd expect. So the method removes the order information. There are 10,000 images in the data set, and this basically amounts to something like 5% reduction in the file size. Finally, I guess just to show off the method to the full, this method can actually be nested, and some data does have a kind of nested multiset-like structure. So for example, a JSON map, which is kind of like a multiset, can contain JSON maps, so it can be a multiset of multisets. And we compressed some JSON data that we downloaded from the internet using a nested version of the method, effectively a recursive version. And again, you achieve a compression rate very close to the information content of the multiset in this case. So just to conclude then, we've been studying the problem of encoding multisets at a rate equal to their entropy. Current methods are pretty slow. They have compute time which scales with the alphabet size. Our method decouples the compute time from the alphabet size and is much faster. It relies on this idea called BBANS, which I came up with back in 2019. And using this method, we can compress a single multiset at a rate close to the entropy of the multiset. The symbols can kind of be anything. We've at least demonstrated that this works for images, text, and multisets of multisets. So that's it. Thanks very much for listening. You can find me and Daniel online at these URLs and code to reproduce the experiments from the paper here. Thank you.